Hello and welcome back. We'll continue looking at section 3.7 on variation. So now let's look at inverse variation as opposed to direct variation. So the inverse variation, this is when one variable will be getting bigger, the other one will be getting smaller. They'll be being pulled in opposite directions. So here's the equation that we'll use for this. When y varies inversely as x, this means that when x gets bigger, we can see that we're dividing by a bigger number, so y should be getting smaller. So as x gets big, y gets small. Or likewise, if x were to get very small and we're dividing by a very little number, this fraction will get bigger. So again, when one decreases, the other will increase. So again, this is varying inversely as one another, or y is inversely proportional to x. So let's look at an example. The length of a violin string varies inversely as the frequency of its vibrations. So if we stop to consider this for a second, let's say that the length of a violin string, let's call this script L, and the frequency that it vibrates at, how fast it goes back and forth, is going to be f. So the length of a string varies inversely as the frequency of its vibrations. So as the length increases, you take a longer and longer string, it vibrates slower and slower. As L gets bigger, F gets smaller. Or if we take a really short string and we pluck that, it's going to vibrate very fast, and we're going to hear a very high pitch coming out of it. So what we have is that the frequency is going to be K divided by L. As L gets bigger, the frequency goes down. As L gets smaller, the frequency will go up. A violin string that's 8 inches long vibrates at a frequency of 640 cycles per second, meaning that it's going back and forth 640 times each second. So the question is, what's the frequency of a 10-inch string, one that's slightly longer? So we have our equation here. F is the frequency, L is the length of the string, K is some unknown constant, but we can figure that out. A string that's 8 inches long, so 8 inches long, is going to vibrate at a frequency of 640 cycles per second. So K here is going to be some unknown number. But we can figure out K. If I multiply both sides by 8, I'll have K is going to be equal to 640 times 8. And this is going to be I'll have to do some mental arithmetic here. 640 times 8, 2, 3. Turns out I can't do math. 5,120. So if we plug everything back into our equation, the frequency a string vibrates at will be 5,120 divided by the length of the string. So if we look at try to find the frequency of a 10-inch string, so just a little bit of intuition before we actually plug this in, a violin string that's 8 inches long vibrates at a frequency of 640 cycles. If we're at 10 inches, we've increased the length, and because these are inversely proportional, we should decrease the frequency. So let's find out how much the frequency will have decreased. So the frequency will be 5,120 divided by the length, which is 10, which is going to be 520, and this is cycles per second, which are also known as hertz. So we went from 640 hertz to 512 hertz. So we decreased when the length increased, and everything is sort of fitting together. So this is quite nice. Now, it can be that there's more than just two variables. And we can have combined variation where we have both inverse and direct variation occurring at the same time. So just as a quick example, let's say we're working for some company and monthly sales S varies directly as the advertising budget and inversely as the price of the product. So if you spend more on advertising, the sales increase. If you increase the price, the sales decrease as fewer people want to buy it. So if we think about these individually, S will vary directly as A, meaning that S is going to be equal to some constant times A. As A increases, S increases. As the advertising budget increases, the sales increase. But S varies inversely proportional to the price, meaning that if we increase the price, the sales will decrease. So if we want to combine these together, we do so in essentially the obvious way, which is going to be, S is going to be K, A is going to be on the top of the fraction, and P is going to be on the bottom of the fraction. As A gets bigger, S gets bigger. As P gets bigger, S gets smaller. So we just combine everything into one equation right here. Roughly, the way that I approach this is whenever something varies directly, we want to put it on top of the fraction, and when something varies inversely, it's going to be on the bottom of the fraction. And this will hold true no matter the situation. So the number of minutes needed to solve a problem set is going to vary directly as the number of questions and inversely as the number of people. So let's take a second to parse this. The number of minutes needed to solve a question is going to vary directly as the number of questions. So the more questions there are, the longer it takes to solve all of them. Makes sense. It will also be inversely proportional to the number of people that are working on the questions. So if you have more people working on the questions, it should take a shorter amount of time to solve them. Okay? Everything seems to make sense. It gives us some numbers. It takes 4 people 32 minutes to solve 16 questions. How long will it take 8 people to solve 24 problems? So let's write down our equation and plug and chug. So the number of minutes needed to solve a problem set. So this is going to be time in minutes needed to solve the question. So the number of questions I'm going to call n. This is the number of questions. And the last one will be, I'll call P, which is going to be the number of people that are working on the questions. And T is going to vary directly as the number of questions. So we'll put that on the top of the fraction, and we'll put the number of people on the bottom of the fraction because it's inversely proportional to the number of people. So again, directly means on top, inversely means on the bottom of the fraction. It takes 4 people 32 minutes to solve 16 questions. So if I have my equation here, 4 people, it takes them 32 minutes to solve 16 questions. So I put everything in the right spot. 32 minutes for T, 16 questions for N. P is the number of people, so it's going to be 4. Which, if I solve this for K, if I simplify this, we'll get 32 is going to be equal to 16 divided by 4 is 4. And if I divide both sides by 4, I get that K is going to be equal to 8. So far, so good. So now my equation looks like T is equal to 8 times the number of questions divided by the number of people. So how long will it take 16 people to solve 24 problems? So the time is going to be 8 times the number of problems, which is 24, divided by the number of people, which is 8. 24 divided by 8 is 3. And 8 times 3 is going to be 24. So my final answer is going to be 24 minutes. It takes 8 people 24 minutes to solve 24 problems. And so here we had combined variation, meaning that we're going to have sort of a direct relationship and an inverse relationship between some variables. But we don't have to stop at 2, and they don't have to be mixed as in one direct and one indirect. Joint variation is when both variables, when two variables will vary either directly as a product or inversely as the product. We're going to focus on this for the moment. So joint variation is going to be when a variable varies directly as the product of 2 or more variables. So let's focus on this equation right here. Y is going to be equal to k times x times z. So we can see that as x gets bigger, y will get bigger. But also, as z gets bigger, y gets bigger. So y will vary jointly as both x and z. So y varies directly as x and directly as z. So we say that they're joint. This is an equation from physics that you may have seen before. The force of gravity is going to be equal to some constant, so g is just going to be some number, times the product of 2 masses divided by the distance between them. So if, for instance, m1 is the mass of the sun, and m2 is the mass of the earth, and d is the distance between them, we could plug all that in here to figure out how much force is the sun pulling on the earth with, and vice versa, how much force is the earth pulling on the sun with. And the thing that I want to point out here, I don't think we'll use this equation directly in this video, the force of gravity is going to vary directly as both m1 and m2, the mass of our 2 objects that are pulling on one another. So F is going to vary jointly as m1 and m2. But it will also vary inversely with the square of the distance between them. So we can see that this entire relationship, F is just going to vary directly as m1, so as m1 gets bigger, F gets bigger. As m2 gets bigger, F gets bigger. As d gets bigger, since it's on the bottom of the fraction, F will get smaller. So let's do one final question very quickly. The volume of a cone varies jointly as the height and the square of its radius. So let's write down an equation. V is going to vary as h and the square of its radius r. It's going to vary jointly, so it's going to vary as the product of h and r squared. Okay, so as the height gets bigger, the volume gets bigger. As the radius gets bigger, the volume will get bigger. So it's varying directly as both of these jointly as h and r. So we know that a cone with a radius of 6 feet and a height of 10 feet has this volume. So let's figure out what our constant is. So the volume is going to be 120 times pi. K we don't know yet. The height we said was 10 feet, and the radius is 6 feet. Simplifying this, this is going to be K will be equal to 6 times 6 is 36, times 10 is 300. It's 360. So if I divide both sides by 360, we'll get that K is going to be pi divided by 3 after I cancel out 120 on the top and bottom. So V is going to be pi thirds times the height times the radius squared, and I can plug in my last numbers here to get the volume of something whose height is 12 feet. Sorry, height is 2 feet, and its volume is 12 feet. This would just require a little bit of simplification, but there you have it.